Good morning, folks, and welcome to the Foreign Press Center. We're pleased to have all of you here today for this briefing on climate change in the Arctic. We are joined today by two experts, colleagues from the National Oceanic and Atmospheric Administration, Dr. Jeff Key and Dr. Ed Farley. They'll be talking first about their research related to Arctic climate change, and then after that we'll go on to your questions. Our first speaker this morning will be Dr. Jeff Key. He's the branch chief for Advanced Satellite Products Branch at the Center for Satellite Applications and Research, which is part of NOAA's Satellite and Information Service. And his topic is Observing Arctic Climate Change from Space. Dr. Key.
Thank you, Mike. I'm happy to be here and have this opportunity to speak briefly about how we use satellites to observe the Arctic and perhaps more importantly, what we've learned about Arctic climate change looking down from space. As you can see here, one of the themes is that what happens in the Arctic doesn't stay in the Arctic, and I'll address that theme throughout the rest of this short presentation. So first I want to spend a little bit of time showing you what the Arctic looks like from space in various ways. And this is an illustration that doesn't really show us what the Arctic looks like from space because it's a composite of different types of satellite data made specifically to eliminate the atmosphere and let you see the surface. So you don't see clouds here, which of course you would see from space. But what I like about this illustration is that it makes the point very clearly that the Arctic is an ocean surrounded by land, which is very much in contrast to the Antarctic, at the opposite end of the Earth, so to speak, which is a continent, which is land surrounded by ocean. That has significant implications for the reaction of the two polar regions to changes in global climate. So here we're only talking about the Arctic. This is perhaps more a better view of what the Arctic would look like from space, without all the labels, of course. But here we see clouds and sea ice and the Greenland ice sheet down there in the lower left. We see some snow-covered land and snow-free land, and this gives a good flavor of the complexity of the Arctic climate system. From space, we can look at very high resolution to see the very fine details of the surface if we want to. Here you can see sea ice at a pretty high resolution, about 250 meters. We have higher resolution instruments than that. But here we see ice flows. We even see the little ridges on the ice flows, and we see ice with different thicknesses between the flows. Zooming back out a little bit and moving over land, we use satellites to monitor glaciers, alpine glaciers. We can measure their area, their movement, and their change over time, and of course snow cover as well. And then zooming way out, we can combine many different satellites from many different countries, some of your countries, and U.S. satellites as well, put them together to get a very nice picture of atmospheric circulation around the North Polar region. What you're used to seeing from satellite, particularly on the weather reports on television, is visible data, something that you would see with your own eye. Sometimes you see infrared data as well. The problem is, in the polar regions, with all the snow and ice, it's difficult to determine the properties of those physical parts of the system and distinguish them from clouds, for example, in just the visible part of the spectrum. So we need to look at the Arctic and the Antarctic with what I'm calling here alien vision, meaning something beyond the visible portion of the spectrum. Near infrared, infrared, microwave. And in microwave, we have passive microwave, which is just what our bodies are emitting at a very long wavelength, and active microwave, which we know better as radar, where we send a signal down from the satellite and measure its return. And with all of these different types of data, we can determine snow properties, ice thickness, cloud particle sizes, not every single little particle, but overall, and so forth. We also need gravity. Gravity is very important for Arctic climate change and also for Antarctic climate change because it tells us the difference, how the ice sheets in particular change over time, but it can also tell us how snow cover is changing. So the first point I want to make is that a comprehensive space-based observing system needs a multitude of satellite sensors, and no single space agency, not NASA, not NOAA, not JAXA, not EUMETSAT, provides all of the sensors that we really need to robustly observe the Arctic. So we need international partnerships, and I think NOAA has been very good about forging those partnerships and needs to continue doing that in the future. From satellites, we measure very basic information. It's upwelling radiation, not dangerous radiation, but visible, infrared, microwave radiation. We need to turn that into something that we can use to study changes in the Arctic climate system, like snow cover and ice cover, as we see here in this animation. And we estimate many different properties of the physical system, as I have listed here, including cloud properties, ice thickness, sea ice thickness in particular, atmospheric chemistry, winds, for example here. Many different things that I don't have time to show. So the second point I want to make is that we estimate many properties of the physical climate system from space, and all of these have operational applications. We use sea ice for shipping and for oil and gas exploration. We use information about the atmosphere as well as snow cover in numerical weather prediction all over the world. But all of these properties also have climatological implications as well, and we use them in climate studies. Probably the most popular trend in the Arctic that people have seen over the years is how sea ice cover has changed. We all know that it's been decreasing. That's not new news. That's, in some sense, old news. What's perhaps newest about it is that we've had record minima in the ice cover in 2007 and again in 2012, and then a fairly significant rebound in 2013 and 2014. But the trend is still downward. What's newer, and what I'm not showing here, is that we have new products from space that estimate sea ice thickness. And we've applied one of our own products to 30 years of data, and we now know that not only has the Arctic ice pack been thinning, but we know exactly where and in to what magnitude, in what degree, over the last 30 plus years. So that's new information we're very excited about, and we'll continue to monitor that into the future. From space, we also observe how the atmosphere is changing. Winds, chemistry, temperature, humidity. Here's an example of how winds have changed. We know that the polar jet stream has shifted. It's strengthened somewhat over Eurasia, but weakened over Canada. What's important about that is that this affects mid-latitude climate. As the jet stream weakens, it tends to meander more, and we get more extreme weather in the mid-latitudes. So here's another example of what happens in the Arctic isn't staying in the Arctic. Vegetation has changed. Plant growth has increased up to 10% in some areas. It's not just getting greener, it's changing in character. So if we replace tundra vegetation with shrubs, for example, that changes how much sunlight is reflected, and there can be a feedback effect where actually a change in vegetation can lead to even greater warming, which leads to a greater change in vegetation and so forth. The last point I want to make is not about changes in individual properties of the climate system, but from space, by combining many different types of satellites, we can also look at how the different components of the climate system interact. And what we've learned very recently, and haven't even published this yet, is that changes in wintertime cloud cover can affect summertime sea ice. And that's hard to grasp because we're talking about a difference in time of 7 to 9 months. Look at the cloud cover outside now. Can you predict what's going to change, what effect that's going to have 9 months from now? Very difficult, but we found a very strong relationship about how clouds in the winter affect summertime sea ice. This will help us improve short-term sea ice forecasts. So the fourth point I want to make is that satellites can be used not just to study individual properties of the climate system, but also the feedbacks and interactions between them. So what does all this matter? Well, changes in sea ice impact shipping, fisheries, as we'll hear from Ed Farley in the next presentation, coastal erosion, wildlife, and weather, as I've just pointed out. Changes in snow cover impact water supply, which is very important to many, especially arid countries. Also weather, agriculture. A warming Arctic means a thawing permafrost, which impacts infrastructure. And of course, the big one is that melting ice sheets cause an increase in sea level or sea level rise, and that'll impact any coastal city anywhere in the world. So again, Arctic processes affect global climate. What happens in the Arctic doesn't stay in the Arctic. Satellites have been critical, essential to discovering, monitoring, and quantifying changes in sea ice thickness, that's new, plant growth, changes in circulation, melting of ice sheets. And we're also using satellites to look at relationships between parts of the climate system. Sorry, that was mine. And a new discovery, I think, is that clouds have actually been reducing the magnitude, or reducing, holding in check the magnitude of Arctic warming. The way clouds have been changing over time has actually acted to reduce the amount of warming that's occurring in the Arctic, and that's a very important point from a climatological perspective. Once again, we need lots of different satellite sensors. No single U.S. agency or any agency in any other country has all the sensors we need. We need to continue to promote, facilitate international partnerships. Now, having said all that about satellites and how great they are for observing the Arctic, we can't see everything from space. And in fact, we'll hear about one aspect of the Arctic climate change that we can't hear in a minute from Ed on fisheries. Thank you.
Thank you very much. Our next presenter this morning is Dr. Edward Farley. Ed is the Ecosystem Monitoring and Assessment Program Manager at the Auk Bay Laboratories, which is part of the NOAA Alaska Fisheries Science Center. Ed.
All right, thanks, Mike. Good morning, everyone. I'm going to jump right into it. The focus of this talk is going to be sea ice impact on fat that's available to fish. So one of the main fish food that we see in this region is zooplankton, and we're going to focus on some of what changes occur between large zooplankton, which you see here, which is a beneficial fish food for fish, and some of the small zooplankton, which I'll show in just a minute. So the focus of the talk here is going to be in the Arctic, which is up in the north in the Chukchi Sea. And again, Jeff just highlighted that decline in sea ice extent in September. I'll go into that in a few more minutes in a little more detail. And I'm going to start with the subarctic, which is in the southeastern Bering Sea. It's that continental shelf down the bottom part of the picture there. And the issue here is sea ice extent and duration during spring and how that might impact the availability of large versus small zooplankton for fish. And one of the things I want to mention that if you're a fish or a marine mammal in this region, you're going to want to store as much fat as possible before winter so you have a better chance to survive during winter. So that's why fat is really important. So I'm going to begin here. And our research has indicated that when we have early ice retreat, we get a plant bloom that's feeding the zooplankton, mostly small zooplankton, and that these small zooplankton have less fat. So early ice retreat is typically related to warming temperatures. And when we have a late ice retreat, usually related to colder winters and colder springs, we get an earlier plant bloom that feeds a different component of our zooplankton. It's the large zooplankton, and we've now found out that those zooplankton have more fat. So if we look into an example, which I'll pull into fisheries here in just a moment, we have a period of time, most recently 2002 through 2005, where there was an early ice retreat. And that area that you see down in the subarctic, which is right down in this region right here. You see from satellite image there's very little ice down there. That's in May 2002 compared with May 2012, which was similar to a period of late ice retreat from 2007 through 2012. And here you can see that in that time period there's ice extending all the way down into that subarctic zone. So one of the major fisheries in the subarctic is our walleye pollock fishery. Walleye pollock have a commercial value of around $500 million annually from 2012 McDowell Group. They're also utilized for fake crab. Many of you may have had that, and premium fish sticks, such as the example I show here. And in that time period that I'm showing here, from 1994 through 2014, we see that there was a downward trend in the biomass, or thousands of tons of pollock that were available in the Bering Sea. That was followed again by an increase. But if we focus on this downward trend, that tended to occur during that early ice retreat period. That drop amounted to a 40% drop in available pollock catch. So that was a big issue. No one really understood why the pollock biomass was declining, but it was impacting the fishery. It was followed then by a recovery, fortunately, and that occurred during what we saw as this late ice retreat period. So as I mentioned before, when we get early ice retreat, we get these smaller zooplankton with less fat. When we get the late ice retreat, we get larger zooplankton with more fat. And this is just an example of some of the zooplankton types. The top 4 are small zooplankton. The bottom 2 are large zooplankton. And you can see just in the figure here, there's about 2 times more fat in the large zooplankton than in the small zooplankton. Not only that, we see there is even a difference in the amount of fat within all the zooplankton types between the late ice retreat and early ice retreat. But the take-home message here is if you're a fish, you want to eat the large zooplankton, you get a better food packet. And if we look at what our fish were eating, these are the young fish that we're studying, we can see that overall in the early ice retreat period, they were feeding more on small zooplankton because they were more populous in the environment that they were swimming in. And then we move into the late ice retreat, they were feeding more on large zooplankton because those large zooplankton were more abundant in that period. And if we all know that you are what you eat, and if you look at the condition of these young pollock in that early ice retreat period, this is a measure of fat. Their fat content was much less than it was in that late ice retreat period. So again, they're feeding on, in this late ice retreat period, better food, giving them more fat, more storage for winter survival. And just to show you, we've related that amount of fat to the survival of these pollock, and we can see there's a nice linear relationship there, just indicating the more fat that they have prior to winter, the better they're going to survive. So the mechanism then is really how ice is impacting the type of fish food, either low-fat fish food or high-fat fish food, and how that fat reserve impacts winter survival, and that drives mortality in that low-fat reserve period, early ice retreat period, versus a high-fat reserve period, which is the late ice retreat. So if we move up into the Chukchi Sea now, into the Arctic, the issue there is declining sea ice extent, as Jeff had mentioned. And this is during September. So if you remove the ice is a reflective surface, and the sunlight then hits that reflective surface. Most of that energy is bounced back up into the atmosphere. But if you have less ice there, you've got water which is darker, and so more of the sunlight's hitting that water, and that energy is impacting the sea surface, the sea temperatures, by increasing sea temperature. So an increase in temperature we're going to find out what might happen with some of the more important species here. And from here we're moving up one level to a fish called the Arctic cod. It's an extremely important fish in this food web. I don't have the plants here, but you have plants that go to the zooplankton, which feed Arctic cod, which again feed these ice seals, which are extremely important to polar bears. And again, in this region, the more fat you store in the summertime gives you better survival for winter. There's also another fish in this region called the saffron cod. So I'm going to give you just an example of some of the research we've done to show differences in these Arctic cod, which are real important, versus saffron cod. A survey we conducted the past couple of years shows that over at the far left-hand corner of the screen that the Arctic cod are extremely abundant in this region of the Chukchi Sea in the Arctic. and more so than the saffron cod. The main issue here is the differences in distribution in relation to sea temperature, and that the Arctic cod tend to be distributed in sea temperatures between about 3 and 6 degrees Celsius, whereas the saffron cod tend to prefer the warmer water in the near shore in about 9 to 12 degrees Celsius. So what's the difference between these two fish that seem to be fairly abundant in this region that are available for ice seals and other marine mammals? Well, the difference is that these Arctic cod have about 2.7 times more fat content than the saffron cod. So if you're an ice seal, you're going to have to eat 2.7 times more saffron cod to get the same amount of fat as you get out of one Arctic cod. We've also done some experiments on growth rate in relation to temperature of these two species, and the one highlight here that I want you to see is the temperatures on the bottom there. It's in Celsius again. But the Arctic cod, that curve is in blue. Their growth rate is maximum at about 7 degrees Celsius, as opposed to saffron cod, where the maximum growth rate is about 15 degrees C. So Arctic cod prefer cold water for growth. In fact, if they get above 7 degrees Celsius, their growth rate declines and they tend to, above 10, begin to die. So warming water is not good for Arctic cod, whereas it's very good for saffron cod. And one of the models, some of the models that we have for projecting temperatures, sea temperatures into the end of the century suggests that that area that we see those Arctic cod distributed in our most recent surveys is going to warm up to about 10 to 13 degrees Celsius, and that is a potential to be too warm for these Arctic cod, so they're going to be moving out, either move out of this region or not make it. So this is some of the information and some of the research we'll be conducting in the future on what the implications of a potential warming in this region might have on this important fish. So the conclusion is, as we continue to warm the Arctic, we expect to see, at least in the subarctic where our walleye pollock are at, more periods in time where there is early ice retreat, and that could potentially impact their food source, giving them lower fat reserves and more mortality. And then and that has a potential implication also for our commercial fisheries. And then in the Arctic, we're still studying this, but this potential warming up there may not be very good for Arctic cod, and that's going to have real consequences for other marine mammals. Thanks.
Yeah, thank you very much. And with that, we'll move on to your questions. Folks in the room, please wait for the microphones. Identify yourself and your outlet. Folks in New York, please step up to the podium and we'll see you on our monitor. And for anybody who's watching via live stream, you can email your questions to Monica Allen, that's MONICA.ALLEN, at NOAA, NOAA.gov. With that, we'll get started. We have a question here in the front.
Yes, Seth Borenstein, Associated Press, for Dr. Farley. If you're looking at the difference between, let's go to the Bering Sea part, early and late spring retreat. First, can you define what time frames you're talking about? I mean, what dates, what is your baseline for early and late? And if this is connected to anthropogenic warming, why, when 2012 you had record low sea ice extent, you had late retreat? I mean, can you walk us through the connection between early and late retreat and warming, since you seem to get both during warming years, which is a little confusing?
Is it okay for me to put that slide back up? It'll be easier to...
Absolutely.
It's a nice cartoon to speak to, and I went through it very quickly, hoping someone would ask that question. All right. So, early ice retreat, a later spring bloom. This is the plant bloom. I don't know how many people have plants, but we know that they take fertilizer or nutrients, and it takes sunlight to get your plants to grow. Typically spring is a time when plants begin to grow, and it takes the fertilizer helps that plant grow. But here in the marine environment, it also takes a stable water column. So if there is no ice in that region. I don't know how many people know about the Bering Sea, but it's very windy there. So when you have a lot of wind, the water columns being mixed up, it isn't until later on in the spring, around May, when the wind begins to die down. As soon as the wind dies down, well, then you've got your nutrients in place, the sunlight's in place, and that's when what we call phytoplankton, or the plants that are feeding the zooplankton, that's when that bloom takes place. And that later bloom tends to favor these smaller zooplankton species. If we have a late ice retreat, that means the ice is extended down into the subarctic or the southeastern Bering Sea in through spring. When that begins to melt back, typically in March, it creates a freshwater lens over top of the seawater. That lens tends to help stabilize that water column earlier. And that earlier stabilization, we've already got the nutrients, we've already got a lot of light. March is very light in Alaska. And the bloom begins to occur earlier, and that early bloom favors these larger zooplankton species. Now, about the variability. All the climate models show a lot of variability around a trend. So if you're looking at the trend is for an increase in temperature, but there's always going to be a lot of variability around that, and that occurred most recently. So we had 2 through 5 was some of the most warm and early retreat sea ice years we've ever seen. And then we had 7 through 12, which were very cold, and again, that brought us back to that colder time period, and again, that variability around these climate models.
The 12 was a record low. I mean, record low sea ice. 2012 was a record low sea ice. That's warm. That's where it's. Yeah, you've got me confused here.
I get it. Okay, so now we're connecting between ice up in the Arctic and ice that occurs during winter, which occurs every winter, and can move down into the subarctic or down into that eastern Bering Sea during winter. That's typically Jeff's probably going to have it's 1 year ice. That's very thin ice. That ice will melt back very quickly in the summertime. And so what we're getting at there is the amount of multi-year ice up in the Arctic is declining. We're getting more years with 1 year ice that just occurs over winter. It's thinner. That ice melts back quicker. But it doesn't mean it doesn't advance in the wintertime. It can. If it's really cold, it'll advance down to the subarctic zone.
And what is it right now?
It's warm. It's warm in the subarctic. Extremely warm.
So is it a late or an early retreat?
It'll be an early retreat. In fact, it looks a lot like 2002 through 5. It started last year.
Jeff, did you have anything you would like to
I
add?
can just add one thing to the last point, that this February had the earliest maximum ice extent in the Arctic on record, in the satellite record. And what that means is that that the peak of the ice cover occurred a couple of weeks, 2 to 3 weeks earlier than normal. And it's also the minimum maximum ice extent, wintertime ice extent. So that in part answers your question about what's going to happen or what's happening right now. We had less ice this winter in the Arctic than any other winter during the satellite era.
Wait for the mic.
Thank you. Savin Jasmankazeh, Azerbaijan. I just wonder, based on this study, are you proposing or recommending any specific measures that would improve the preparedness for these climate impacts, for foreign governments?
Talking about fish? Fisheries in particular, or just in general?
Well, for better prepare, yes, based on what we already know and the worsening climate impact, is there anything that you would suggest, concrete specific measures that would help the preparedness?
If you do global shipping, get some ships that are good in the Arctic because you'll have more shipping routes. I say that somewhat in jest, but it's true. I think perhaps more directly, particularly for arid countries, would be predictions of snow cover, because that affects water supply. I mean, I couldn't tell you what to do, how to prepare better, but the more information we have about changes in the Arctic, the better we'll be able to predict the next season's snow cover, for example, alpine snow cover. And from that, you can then perhaps adapt or mitigate the impact on agriculture and your water supply. So I think that's becoming increasingly important. Fisheries, I don't know if there's anything you can do to adapt to changing fisheries in the Arctic.
Yeah, the only thing I can add to that from the fishery side is that NOAA's mission is to be as good stewards of our marine resources. And saying that means that we take very seriously our stock assessments of the available fish for commercial harvest. And within those, we're trying to include information on how climate change and variability might impact available fish for commercial harvest. So those are the additional items, such as we saw here in the way that there's a decline followed by followed by a recovery, really had no mechanism initially until we started to look at some of the implications of what was happening within the fish's ecosystem that they're swimming in and what it meant for their the types of food that they're preying on.
If I can add one more thing, not about fisheries, but back to what I was saying before. We've been talking about the Arctic, but of course another important part of what we look at in the Arctic, which is the cryosphere, snow, ice, permafrost, is another part of the cryosphere is global, occurring in approximately 100 countries. And another area of interest for us outside of the Arctic is what we call the third pole region, the Himalayas. And this, of course, would be very important. Changes in the Himalayas is very important for all the countries surrounding the Himalayas, from China, Pakistan, India, and so forth. And so both satellite work and just generally climate work is very important in that region. And I mention this because the contribution to sea level is, well, there's something called thermal expansion. The fact that the oceans are simply getting warmer makes them expand and makes sea level rise. That's the biggest contributor. But in terms of freshwater input to the ocean, it's actually not from the ice sheets. The major contributor is glaciers. And it's alpine glaciers, mountain glaciers. And that's because glaciers occur in warmer areas primarily, like the third pole region. So melting of glaciers is going to impact water in the third pole region, in the Himalayas is going to impact water supply and agriculture in those areas. So the better observations we have of changes in that region, as well as changes in the Arctic, the better we'll be able to predict the impact on society.
So guys, do we have any other questions from the folks here in the room? Because we do have one here in the back from Laurie.
Hi, I'm Lauri Tankler from Estonian Public Broadcasting. Besides, having more routes in the Arctic and the changes to probably the fish that the fisheries are going to be pulling out of the, what are some of the other impacts you said we may be able to predict better when we're also watching the third. The Himalayas and so on. What are some of the other impacts that you see from this, pretty drastic thing, and this year being with the least ice in the Arctic region?
We've been asked to stand up, so I'll do that. There are many. There isn't any one in particular, I think, that's going to impact Estonia so much. But, and I know it sounds like I'm just waffling on this, but I'm not. The impacts are not just on climate, but also from a weather perspective. So one thing, for example, I just mentioned, we need better observations. And that sounds like a line that you would hear from anybody, but it's actually true. And it started with our work on polar winds, where it was determined by weather services, weather prediction centers globally, that errors in the wind field in the Arctic significantly impact mid-latitude weather forecasts. And even more than that, by having better wind information in the Arctic, we have better hurricane track forecasts. Now, okay, you don't get hurricanes in Estonia, but my point is that that's one aspect of observing the Arctic that's important globally, not just in the Arctic. The other is now back to your question about climate change. Well, there's sea level rise that's going to impact all areas, and it impacts them differently. And I know when people hear that on average we're seeing a 1 millimeter increase in sea level per year, what's the big deal? Well, the big deal is that over time that's going to add up, and it's going to be different in Estonia than it will be in London, for example, and even different across the English Channel, and different for New York. But over time that builds up. Shipping routes you mentioned, so I won't say it again, even though I just did. Fisheries, Ed talked about. What am I missing? It's the best I can do.
Ed, do you have anything you'd like to add?
No.
Okay, great. Any other questions from the folks here in the room? Because I know we have some from email. So Monica, if you'd like to wait for the mic and then go ahead with the first question.
Sure. Hi, everybody. This is a question from Margot McDermott, and she's from Canadian Broadcasting Corporation in Ottawa. Are the changes that have been described today to the fish health and food also happening in the Beaufort Sea, and can this be applied to the Canadian Arctic Ocean?
That's a very good question, and unfortunately I'm unable to answer that for the Beaufort Sea. We've not had, in terms of NOAA fisheries, we've not done a lot of surveys looking at the food web or fisheries within the Beaufort Sea. But I guess I could refer that to Kate, maybe to follow up to see if there are other folks who might have more information on what is occurring in the Beaufort.
Margot, if you'd like to email, you have my email address, I know, so you can email that question to me or to Monica, and we'll go ahead and we'll get answers for you on that. Sorry, Jeff.
I can't say anything about fish. I eat fish, and that's all. But the Beaufort Sea, I will say, I mean, obviously must be changing. I'm just speculating about fisheries, but the biggest changes in sea ice are in the Beaufort Sea. And we see that in many different ways, ice thickness, ice extent, and so forth. So one could infer that there would be some impact on fisheries based on that alone.
Oh, we have another question here in the room. Jane.
Thank you. My name is Hong Zhang. I'm from China's Haixi Media. Can you speak more specifically on the potential impacts that would have resulting from increasing shipping routes across the Arctic? Thank you.
Well, since I said that, I guess I need to answer that. I can't, because I don't know anything about the economy of shipping or even, and I don't think I could put up my slide again because it was a different presentation, but you do see two potentially new shipping routes which actually have been realized. I mean, people have used these new routes, and we can expect those shipping routes to remain open in the coming summers. Not necessarily every one, because as was pointed out earlier, there's a lot of variability in the sea ice even in the summer, but we're moving towards potentially ice-free summer, ice-free Arctic by, say, 2040, the year 2040, something like that. Of course, the models tell us different things. And so I think there would be an increase in the frequency with which those shipping routes could be used. But what the impact of that would be on China, I can't say.
Not necessarily on China, but on the ecosystem.
Oh, on the ecosystem.
Yeah, something like that, or the weather, climate.
Yeah, well, weather, this is something under intense study right now, not so much by me but other people in NOAA. The feedback of the lack of sea ice or the decreasing sea ice extent on the weather systems. I mean, we've been looking in a way the opposite direction, where how does global climate change Arctic weather? But I did mention the point about the changes in the jet stream. And we do see impacts of decreasing sea ice cover on, say, cloud cover. Now, it's a little bit harder to go to the next step of how a smaller, lesser ice extent in the Arctic is going to impact large-scale circulation, but those connections do exist. Again, it sounds like I'm just passing this on to complexity, but it is a very complex system, and the feedbacks are not well understood. For example, clouds that I just talked about, not exciting to you, pretty exciting to me, particularly because they have such an impact on sea ice, as well as the other way around. Changes in sea ice impact clouds. So I think less sea ice is certainly going to change weather patterns, open up for shipping, oil and gas exploration. It's going to be a different world out there, I think, in 20, 30, 40 years.
Increased shipping is a major concern, especially through the Bering Strait and up into the Arctic and eastward. And the reason that is we're really not prepared if there's any sort of accident, at least off the United States exclusive economic zone. If there happen to be traveling in there, there's not a lot of infrastructure in that area for handling any sort of accident, including any kind of oil spill that may occur if a ship is moving through there. And also we have indigenous people in Alaska, Alaskan natives, that rely on subsistence harvest of marine mammals, whales, seals, and they rely on the ice to make all this occur. But if there's increased shipping, that could disturb some of the marine mammal behavior, might impact their ability to take whales. So those are some of the concerns.
I know we have another question here in front, Seth.
Seth Borenstein, AP. Actually, just a few here. Going back to this. First, I guess, Jeff, you said this was the earliest spring, peak. Is this the earliest ice retreat that we've seen, or do we not know yet in terms of this year? And looking at this year, can we both of you just concentrate on? Can you give us sort of more detail of this spring? When was the peak? When is the normal peak? What does that mean for the rest of this year? What are you expecting this year to be like up in the Arctic because of what you're seeing, and especially in terms of the pollock there? And also, Ed, is what you presented in a journal or peer reviewed anywhere?
Basically, all of the peer-reviewed journals are listed down at the bottom of the slide.
Oh, my eyes aren't that good.
Oh, okay. But yeah, if you get a copy of it.
Share the PowerPoint with you guys afterwards. Yep.
I'll just briefly say that, answer a couple of Seth's questions. This is, the peak was February 25th, I believe. The normal peak, this is in the Arctic ice extent, is mid-March. I don't have an exact date. A lot of the change actually was in the Bering Sea region. I don't have an illustration with me, but I can point you to our website. I lead an activity with the World Meteorological Organization called the Global Cryosphere Watch. We have a website which is simply globalcryospherewatch, one word, .org. And I did just put an assessment of the winter 2014-15 sea ice cover. I just posted that a few days ago, actually, and I think it has a nice video illustrating where we're missing ice, basically, this winter. So that would give you the illustration that you need.
I'll just focus on this picture again right here. That's May. This is what we saw in April on the left, the early ice retreat side. So there was very little ice even in what we would call the Arctic, which is just up there above of that subarctic southeastern Bering Sea region, and that was in April. So it's extremely warm in the subarctic southeastern Bering Sea this year. It was warm last year, so we're seeing back-to-back years where it's warm again. And last year we started to see, in our survey, a shift in that ecosystem back to smaller zooplankton. And now typically we haven't been doing annual surveys lately, but because this issue is so important to our pollock fishery, we're headed out again this summer to get a better understanding of what this continued warming is having on the fish food and what that means for pollock.
Another question in the room?
Hi, this is Meng from China Central TV. I have a question for Dr. Farley. I just came back from Alaska last month, tried to catch some Eskimo whaling stories, but we didn't actually see the catch a whale. So does this also impact on the whaling communities?
Yes, loss of sea ice up in the Arctic does impact whaling. They use the ice as a transport mechanism to get them offshore, and then use leads where the ice has broken up, where you've got water, typically where the whales are located. So if there is less ice or less what we call multi-year ice, the ice is thinner, and it's more difficult for them to get out into the ocean, and using that ice is one of the ways that they do that. So if you didn't see any whaling activity, it may have been related to just as Jeff pointed out, just the low ice amount this year. That is impacting their ability to get whales.
How could they delay the time of the whales come back every year? I mean, how could they change the time of the whales come to the same point every year?
I was just at a meeting about 2 weeks ago, and there was a fellow there from Barrow. So this is late April. And he said that he's one of the captains, whaling captains. And he said that his son, it was just at that point going out. So I don't know when you were there, and I don't know what that means in terms of the timing, but he was just talking about the difficulties because of the sea ice is very thin, and for them to get their machinery out there and then their boats to get into these open leads so they can get whales. I don't know what their normal timing for whaling is, but they were attempting it at least in late April.
Another one here in the room. Sorry.
Thank you. I just wanted to follow up. You briefly mentioned that it's going to also impact oil and gas exploration. Could you please elaborate on that?
Well, I just simply meant that if there's less ice, oil and gas exploration would be easier to achieve. It's a little bit more than that, because more information in the Arctic would allow us to do better weather prediction in that area, and weather prediction is obviously very important to oil and gas exploration. But all I really meant was less ice, more open water, easier to get the equipment that you need in for oil and gas exploration.
More or less?
Well, I'm not really familiar with the area, but I would guess more. And you know, a longer period during the year when you can when you have oil and gas exploration operations going on.
We had at least one more question from the internet. So.
Thank you. Okay, this is a question from Craig Welch, who writes for National Geographic. He would like to ask Ed Farley to explain in greater detail how declines in walleye pollock or Arctic cod reverberate through the food web in those areas.
I'll start with Arctic cod. So we're going to continue to do research on Arctic cod. We know that they're there, they're highly abundant, and they're extremely important in the food web. And that food web includes ice seals all the way to polar bears. And obviously polar bears are an issue. They're reliant on sea ice to capture ice seals. And I don't know if anyone's read lately, but more polar bears, because of loss of sea ice, are resorting more to land-based food. And that land-based food has been determined as more junk food. It's not as high in fat content as their normal prey as the ice seals are. And so, again, polar bears, they provision themselves in summertime, and that's when they need to be on the ice, feeding on ice seals. And those ice seals that feed on these Arctic cod need good fat components to make sure that they've got enough fat to make it through their life. Now, walleye pollock, at a very young life stage, when you're at the small walleye pollock stage, they are preyed upon by other fish in the subarctic in the southeastern Bering Sea. One of those fish, especially when it gets warmer out, these young pollock tend to change their distribution vertically in the water column. They get more towards the surface, and Pacific salmon, such as sockeye salmon from Bristol Bay, tend to feed on them heavily. Other fish species that feed on walleye pollock are arrowtooth flounder, but there's no commercial fishery on arrowtooth. So there are a lot of walleye pollock in the Bering Sea, and they're an extremely important component of a lot of other fish food web.
Attempts by some in Congress to stop NASA from studying the Earth. If successful, how will these attempts affect NASA's research in the Arctic? I'm not sure that Emily knows. We're NOAA, we're not NASA, but will cutting down on that Arctic research be detrimental in any way?
Yes, I think so. I'm not going to talk about the politics of the budget, but I mentioned partnerships, and it's not just international partnerships, it's interagency within the U.S., and that means NASA and NOAA. And you couldn't see it probably on the slide that I showed. One half of that slide had NASA satellites. And we rely on those. There are satellites that NASA flies that nobody else does. They're not part of NOAA's operational satellite fleet. I'm referring in particular to cloud radar and cloud lidar, the gravity instrument, GRACE. These are NASA satellites, not NOAA satellites. Now, I don't know if budget cuts are going to impact those satellites specifically, but they would impact follow-ons. So yes, I think it would have a huge, huge impact. Again, I know you're probably not excited about clouds. I am. But these cloud instruments are particularly important in the Arctic because it is very difficult to remotely sense the cloud properties from space when you're talking about clouds over snow and ice. And these active instruments like cloud radar and cloud lidar are just essential for doing that. Gravity for studying the ice sheet mass balance changes and so forth. So yeah, I think it would hurt.
We have another question from CBC in Canada, and this is for Jeff Key. You said, Jeff, that the biggest change to ice extent is happening in the Beaufort Sea. Can you briefly explain this, and have they seen anything significant in the past few years?
Yeah, well, we've seen, okay, can I explain why the biggest change is in the Beaufort Sea? Not entirely. I can say that it seems to be connected to something called the Pacific Decadal Oscillation. So that side, the Alaska side of the Arctic, I think has a lot of activity happening, not just in the Arctic, but at lower levels that's impacting the Arctic. What was the second part of the question?
Sorry.
Oh, you lost it.
No, I got it here. Briefly explain this, and have you seen anything significant in the past
Oh, yes,
few years?
yes, thank you. Have we seen anything significant in the past few years? Yes. The variability I mentioned in the Arctic over time, interannual variability is huge. And we saw a record minima in the ice extent in 2007 and again a new record in 2012. But then I mentioned the big rebound in the Arctic ice cover in 2013. That was largely in the Beaufort Sea. Beaufort Sea, Chukchi Sea, that part north of Alaska is what we're talking about. Western side of the Canadian archipelago and over to the East Siberian Sea. That seems to be a hotbed of activity, and it's also where we see big changes in cloud cover. So that's a very active region, highly variable from year to year. And if you think about it, the North Pole is, the ice over the North Pole is going to be less variable just because that's the coldest part. But yes, the Beaufort Sea has seen tremendous changes over the last few years, from one year to the next, in very opposite swings, which we're trying to explain.
I think we have one last question.
We have one last question from The Guardian, from Rose Hackman. What are the potential human costs to this beyond the indigenous communities that are being affected by increased shipping routes? Are there jobs at risk affected by a threatened fishing industry, for instance?
Same kind of thing you said about.
So this is beyond the indigenous, and are there impacts on fisheries for shipping through the Arctic?
Jobs in commercial fisheries beyond the indigenous fisheries.
Currently, within the United States exclusive economic zone, there is a fishery management plan. It's called an Arctic Fisheries Management Plan, and within that they've identified 3 species of potential commercial fish. That includes Arctic cod, saffron cod, and snow crab. But right now there's a moratorium on fishing. There are no commercial fisheries occurring in the Arctic at this time, at least within the United States exclusive economic zone. So at this point there would be no impact on fisheries.
I don't see any more questions. So, yep. So with that, we'll go ahead and wrap up. Thank you all very much for coming. Thank you, gentlemen, for your insights. And with that, this briefing is closed.